shiver comes down. Oh, she looks so good. Oh, meat and wood, she says so. Now, shiver comes down now. 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 Shiver comes down. Oh, she looks so good. Oh, meat and wood, she says so.
All right, so today is a kind of a one-off. It's a review of the tools that we've looked at so far, along with a demonstration, a tutorial on how to use a proper debugger. The debugger that we'll be using is GDB, and so I'll be walking you through that today. But before we do that, this will be posted on Piazza with the weekly retrospective. That your midterm is on Wednesday when you come back from break. You will have 24-hour window in which to do it. It should only take you maybe an hour or so, like a normal class period. But it will open at 12:01 a.m. It'll go all the way till 1 minute before midnight that day. It's the same format as Exam 1, programming exercises. In fact, there are exactly 3 of them, 3 functions to be exact. And you'll submit them to hand-in. You can use the grader to check them. It's already written up in the books, and I've got an LA that's taking a second look at it to make sure that everything works. You may resubmit it as many times as you want up until the due time, so keep that in mind. And no collaboration is allowed with any individual in the class, outside the class, or ever on the exam. So make sure that all your work is your own. We will be running MOS again. We didn't find too many problems. There were 1 or 2 isolated incidents that we took care of. But for the most part, in the first one, we didn't get any major hits there. We will have lecture that day because I have to come in anyway for other things. But it will be completely optional, as all lectures are. But the format will be going over previous midterms, all right? And we'll be doing a review during the time which you can take the exam if you want to instead of going to the review. You can wait for the review, do the exam after. You can do the exam before, watch the review, and then go back and fix things if you need to, right? So lots of options there with that 24-hour window. Regular help hours will be held. LAs will be there, but they will not give you the same level of help that they would on a lab or a hack. It's worth 100 points, roughly, what, 9% of your grade? But it is not twice as long as the first exam, right? It's just weighted more. All right, questions on midterm? Okay. Again, that will be posted later on Piazza. Coding, software engineering, software development, whatever you want to call it, is a skill. It's a craft like any other, right? Carpentry or woodworking, for example, where the tools are just as important as the actual work that you're producing. And so we've witnessed a lot of tools up to this point in your first semester in the first 8 weeks. For example, you started off with source control and software versioning, right? With Git. Now, there's a long history of version control systems going back 30, 40, 50 years, whatever. Started with CVS, moved on to SVN, and about 15, 20 years ago, Linus Torvalds, the same person that created Linux, it's named for him, decided that he needed to create a distributed version control system because at that point, Linux was just so complex, the ecosystem was so complex, he needed a better software repository system to keep track of it all. And so he put Linux on hold, went over, created Git, and then went back to Linux. And I don't think he's been involved with either project at this point anymore. But why? Well, if nothing else, it gives you a cloud backup, right? For example, your CS50 IDE here is backing up all of your code that you write every second. It's being committed to some repo on GitHub. If you didn't have that and you only had one copy, goodbye, right? If you were working on your own computer and it crashed, oh no, I lost all my files, right? Well, if you were using a tooling system, a source control system like Git, you wouldn't have that problem, right? It's much easier to transfer files and to share files if it's a distributed version control system. Everybody can work independently and have this one copy or a distributed copy among all of them, right? I mean, you're not office drones, right? Use your self-respecting engineers. Use the proper tools for this stuff. Dropbox, Google Doc, OneDrive, those things are for, office stuff, right? Like Word or whatever. Software is much more complicated than a Word document. And so you need a proper system to be able to curate that and to make it auditable, right? You have this entire history, this commit history, that you can go back 5 years and see when was this feature introduced, because now it's causing problems 5 years later, right? There's even a utility called Git Blame, where you can blame somebody for something that bad happened, right? Look up it's Git Blame, and then you're blaming something, right? Anyway, you're not office drones. Like, just putting like even I don't see it too much anymore. Maybe it's there, and I'm not seeing it. But if you want to transfer a file with your partner, you stick in a thumb drive and then you hand it back and forth, right? This isn't 1990, right? Use the proper tools that we have nowadays, right? You've also seen build systems like Make and CMake. You've all probably only seen Make, but it's as old as dirt, right? It's as old as C itself. Because anytime that your code base gets even moderately complex, even the stuff that I've given you for image processing, right? You need a script file that will specify all the dependencies and the builds for repeatable builds. There are also full-on dependency managers. If anybody has any Python experience, you're always installing Python packages. I want to use NumPy. I want to use NetworkX. I want to use this. I want to use that. Right? You have a dependency manager called, a package manager called, anybody? What's it called in Python? Oh no? pip, right? Python or package manager. I don't know what it stands for. But pip install this, pip install that, right? You got exposure to that when you had to install CMaka, right? We gave you the command to do it, but it was apt-get. That's a package manager. It will install stuff. We just told you here, you just use it. You saw how it worked, though. It was all automated, right? That entire kind of it's not a discipline, but it's a job. It can be multiple people on even a moderately large development team, right? The last job, that last real job I had, we had about 100 developers, and two full-time people were devoted to nothing more than DevOps. That's what this is called. Just writing scripts to support the other actual code that's being written, right? Just all the logistics surrounding deploying code, managing code, making sure that it's bug-free, that it's that all the tests get run before it gets committed or pushed out to a production server. All of that stuff is a full-time job for even a moderately large team. And so we had two people completely devoted to that. We didn't call them DevOps back then. but that's what they're called now, development operations. Right? You've seen unit testing. We went from ad hoc testing, right? Does it work? Just compile it, see if it works really quick. Okay, good, move on. If not, all right, go back, fix it, right? That's ad hoc testing, printing it out to the standard output. Then you graduated to informal unit testing, where you were writing code to test your code more rigorously, because that's repeatable, right? All you have to do is hit a button to rerun all of those hundreds of tests that you might have written. And then we graduated finally to a formal unit testing framework. Every single language worth anything is going to have some sort of a unit testing framework with it. Java has JUnit. Python has unit test built into the language itself as a standard package. CMaka was just my choice for this course. There are dozens of other options. CMaka was my choice for this course because it was well supported. It was originally a Google project that was forked off after they abandoned it. And it was simple, easy to use, and it was pretty well standard across different Linux distributions. Those are the decision-making, the criteria that went into my decision-making process for simply just choosing a unit testing framework for a particular language, right? That's the kind of cost-benefit analysis that you'll have to do eventually someday in a job that you're in, right? What language, all right, we're within a framework here. Are we going to use this language or that language or whatever? What tooling are we going to use? Are we going to use that one or that one, right? Evaluating back and forth, even your choice of IDE, right? I gave you this choice simply because it was zero startup, right? You don't have to install anything. You can use it anywhere. You can use it in any browser. All you need is a GitHub account, and that's it. I think back maybe 10 years ago, and everybody was still stuck down in the basement because installing stuff on their own computer was too hard, right? This is the least amount of effort for this course. If you want to see what a real development environment would look like, watch video 1.3, where I set up a VPN so that we can connect to the CSC server downstairs using Samba, so that you can edit code in Atom.io on your computer, compile it through SSH on through an SSH client on the CSC server, and then execute it there, right? Vastly more complicated, right? I mean, if you were in a permanent working environment, you would have to have something like this, and that's where those DevOps folks come back in, right? Typically, you hear stories all the time of somebody starting up a job, and they don't actually get to code for the entire first week because the DevOps are still setting up their machines, right? Because they still don't have access to the repositories and stuff, right? Hopefully, a well-managed development environment and good DevOps would have you up in maybe 24 hours, but you hear stories like that all the time, right? We also we also covered static analysis tools that look at your code before you even compile it. The wall flag, for example. Turn on all the warnings. Turn on some extra warnings. I don't know why they're not included at all. Don't ask me. If I say all, I mean all, right? I don't mean all. And then also the extras, right? Don't ask me. Clang is another compiler that you have access to on your code spaces instance, where you can tell it, analyze my code here, and it'll likely come out with more with the same warnings as GCC does. But once in a blue moon, it will catch things that GCC doesn't. On the other hand, GCC catches things that Clang doesn't either. Right? So if you want a larger tool set here of things to bring to bear to your code, you can also use Clang. Right? Then we looked at dynamic analysis tools. So the only one that we've looked at so far is Valgrind. But you can use that to at least tell where the seg fault is happening. If there's no error on your own computer, but there's an error on another computer, like the grader or something, you can run Valgrind on your computer to show you, no, there indeed was an error. It just didn't manifest itself as a segmentation fault. You were illegally accessing memory on this line, right, with these values, right? You can use it to find memory leaks. And remember, it also has some basic bounds checking. For example, on your array exercises that you were using right now, it will be very, very useful if it would tell you that, nope, you went out of bounds on the array here. The array was only size 5, but for whatever reason, you've got code here that goes to index 11 or index -8 or something like that. It'll tell you, right, if you run Valgrind. But to be able to tell you what line it's on, you need to use that -G flag. And we're going to learn why it's G instead of, well, why not V for Valgrind, right? V is standard for verbose, so it's already taken. But G, it stands for GDB, GNU's debugger, which is what we're going to look at today. Something that we're going to look at much later on is another dynamic analysis tool called profilers for perf testing. Perf testing is just a cool way of shortening performance testing, I guess, right? It's performance testing or perf testing. You run a profiler on your code, like gprof, we'll take a look at that later, and it'll run your code and simulate it and say, 90% of your computation time happens in these two functions. You might want to check that out to see if those are implemented correctly or if there's a way to optimize those, rewrite them so that you're not spending 90% of your computation time there, because it could take something that was running for hours and hours or something, and it'll take it down to a few seconds if you just tweak that function and make it better, right? And to even tell where that's happening, you need to run a profiler. It can also generate, graphical representations of your code, like heat maps. Over here in this section of your code, it's hot, right? That's where you're spending most of your time, right? We might be able to take a look at that later. But today, I want to focus on proper debugging. You should not use poor man's debugging. I tried to, right before the class, I tried to look up the origin of this term, and to my horror, I found a post in 2001 that said that poor man's debugging was better than a proper debugger, and I read it was Ars Technica. I was like, oh God, I hope that this is just because it was 21 years old, because this is the worst advice I've ever read. And everybody kept agreeing with them. Like, oh my God. So no, the poor man's debugging is called poor man's debugging for a reason, because you couldn't afford a proper debugger. It is not at all reliable. What I mean by poor man's debugging is, okay, something's going on. I'll put in a print statement. Okay to here, right? Okay, it runs, and then it dies after that. I'll put in another print statement. It's okay to here, okay to here, okay to here. You put in a million freaking print statements, and then you finally isolate it, and it find out that, nope, it's somewhere else entirely. Why? Because printing goes to the standard output. The standard output is a buffer, like YouTube buffering, right? You start a video and it buffers, it loads up the video, right? It doesn't actually show you every frame at once, right? That's like the printing statements. You have 5 print statements. They're in a buffer. It's not necessarily printed out to the screen yet. It will only be flush. It's called flushing. You flush it to the screen when it decides that it's best to do so, because that's a really expensive operation. So you could have 5 print statements in there. It prints the first one, the third one, but you're already in your code, you're already over here at the 5th print statement where it fails and seg faults out. You never see that because you only see these first 2 print statements. Right? So poor man's debugging is not something you can even rely on, right? And it's now that I think of it, those posts that I was reading were very JavaScript oriented, and there might not be a buffer, and so the console.log is just dandy for them. But and granted, back 20 years ago, there was probably no proper JavaScript debugger. Now you've got that built into every single browser, right? So anyway, we're going to be looking at an old school one called GDB. It is a TUI. So you've probably heard of GUI, graphical user interface programming, right? This is text-based user programming. Now over here in the CS50 IDE, you might have seen this little thing over here with this little tiny bug icon and the play button. They've got a graphical debugger built into this, and if you want to use it, I encourage you to go check it out. I've not run through their tutorial to learn how to fire it up or anything, but I'm sure that behind the scenes, it's nothing more than using GDB. Right? It's just putting nice graphics around it instead. Right? Okay, more spam. Sorry. All right. So, what is a debugger? Well, a debugger is a program that's like Valgrind. It simulates the running of another program and allows you to pause the execution. So, because if you just run a program, right, it'll run and then die immediately, especially if it's short-lived. But you can pause the execution at a certain line or a certain point in the program so that you can take a look around. What are the variable values right now, right? If I print this out, what are the values in that array? What if I multiply x by y? What do I get at this point in the program, right? Then you can step through it line by line, right, and go slowly. All right, everything looks good up to here. Step to the next line. Everything still looks good. Step to the next line. Everything still looks good. So that if you know that it seg faults out on line 42, you can fire up a debugger, set it to stop at line 40, take a look around. What's about to happen, right? And that's what we're going to do today. All right, so to get started, here is the usage of GDB. First of all, just like Valgrind, you have to compile with a G flag. And again, I'm assuming that that's for short for GNU Debugger. Because if you erase all the lines, you won't be able to walk through your code. Once it's compiled without the G flag, all the lines are gone. The G flag preserves metadata, mapping it back to the source code. To run GDB, you just run GDB and then whatever executable you've got. Right? So let's take a look at an example here. I've got some intentionally buggy program right here. Right? All this is doing is asking you, okay, give me a number and I will generate a random array of size, say 4. That's what we're going to start out with. And then I'm going to compute the average of it. I'm going to print out the array, and then I'm going to call this function average that runs over all of them, adds them all up, divides by n, and returns the value, the average. Right? And then we print out the average. Now, if you see the bugs right away, hold off. I want to show you how to find them with a real debugger. Right? So no spoilers, please. Okay? So let's go ahead and compile this. And also, I don't want the compiler giving me spoilers. About half the bugs that I intentionally introduced into this program would be discovered by using the wall flag. Right? So I'm going to use the lowercase w flag to shut off all warnings. Right? I'm going to use the G flag to preserve the line numbers. And I'm going to compile array.originalc. There we go. Right? Okay. Now to fire up the debugger, I use GDB. And then a.out is the executable file that it produced. Right? And it launches up into this text user interface here. I can start typing commands. Right? You see it begins with GDB. I'm in the program GDB right now. Right? Well, it doesn't do much if I can't see my code. Yes, I can see it up here. But as I walk through it, the execution of the code, I'm going to be looking at it down here. Right? So, layout source. Right? And it shows me my code here. I can use the up and down arrows to scroll through it if I want. Right? I can also show other things. Layout next. Right? Ooh, what's that? That's the assembly code. So eventually, if you have to write direct assembly or you have to debug assembly code, you can use GDB to actually look at each assembly line of assembly code. Layout next. Puts them both top to bottom. And now I've got 1, 2, 3, 4 screens already, right? This is why developers always demand at least 2 screens, right? So that they could start separating things and have a wide view, right? A debugger over here, a renderer over here, your code over here, et cetera, right? Your notes over here, right? And then your email sitting up there to check it out when somebody contacts you, or your Discord or whatever, right? Layout. SRC is what we want to focus on, though. SRC is for source. I want my source code. Okay? All right. Well, if I just run the program, it's going to immediately stop because the usage here is that you have to provide a value n. Right? What happened is I didn't provide a command line argument because I'm not at the command line. And so it says usage, you have to provide me a number because I'm going to generate a number of elements in the array. And then it exits with 1. Inferior 1 exited with error code 0, 1, right? Inferior is just its inferior process. A process runs a process, it's its supervisor process and then an inferior below it, right? So what I need to do is I need to set those command line arguments. Set args, and we'll create an array of size 4 so that we can keep it small and we can do the math in our head. Okay? Now I can run the program again. Run. And we see the output here, computing the average of nothing, and the average of nothing is 1. Does it seem to be working? It didn't generate 4 elements, right? 4 random elements. So something's going on here. And by the way, it's starting to show some wear and tear here, right? It's starting to, like lines 35, 36, and 37 here are being interrupted. It's not rendering properly. If that ever happens, you can refresh it, okay? And it'll redraw the entire screen. Right? So I don't know what's going on here. I want to run this program line by line. To do that, I'm going to set a breakpoint at line 24 here, right? So break at line 24. A breakpoint is a pause point, right? I'm going to run the program now, and it will stop at line 24, the beginning of the program. I can step through this line by line now. So next, okay, argc. I'm about to check to see if it's equal to 2 or not. Right? I can go ahead and print that out. Argc. In fact, it's 2. So this should evaluate to false, and I should end up, if I go to the next line, I should end up skipping down to line 28 because this is going to be false. So I could type next, or a shorthand like I did just out of habit there, N is short for next. You can type out the full word next, right, and it'll go to the next line, or you can just go N for next. Right? Next, next, next. Okay? Now, remember what I set my arguments to? I think it was 4, right? So, next, print N. Did it receive the value 4? No, it did not. It received the value 4128, blah, 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 blah. You know what? I'm sorry for the live stream folks here. I should have checked all 9 of you. There we go. There. Now that's in screen. All right? We were being cut off at the bottom there. So is that correct? No, it should be 4. What happened on line 31? Right, so there are 2 arguments here, and so argv sub 1 is my second argument. It should be 4, but can I put 4 as an argument into a number? No. What do you generally do if you want to convert a command line argument like argv sub 1 into an integer? A to I. Right? That's one of those things that the wall flag would have caught. Right? But I wanted to demonstrate this GDB. Right? And there are several bugs still. So I'm going to quit out of GDB because I do need to recompile. Right? I need to recompile, otherwise there are debuggers that allow what are called hot fixes. You go back and you change the code, and it automatically recompiles without you having to restart the debugger. I think that there might be a way to do that with GDB, but it's just as easy to quit and restart it. GDB a.out. Right? I'm back in here, layout, source. Right? And now I know that everything was okay. Now that I fixed this bug, I know that everything should be okay up until line 32. So I'll set my breakpoint at line 32 instead. Right? Set args to 4 and run it. All right, refresh. There. Now we're at that point. Let's make sure that that fix actually worked. Let's print N. Remember, it should be 4, and it is. We're good. We fixed that bug. Okay? Next. Short for next. We go down here. Now, if I just hit next, then it's going to step over that function. I don't know if the problem exists in that function. Right? I want to know if the problem exists in that function or not. If I just go next, it's going to skip. Right? It's going to execute that entire function and be done with it and go on to the next line. What I want to do is I want to step. So let's go ahead and rerun this from the beginning. Yes. Next. Now, instead of going next, I'm going to go step. I want to step into the function. When I do that, I end up at the function itself, random array now. Right? Random array, and I'm allocating memory here. Let me go ahead and go down here, and we can see it without the highlighting. Right? The first thing I do is call malloc. Right? Do you see any issues with that line, first of all? Yeah, size of is not generally used with variable values, is it? Every instance that we've seen of size of has been a int or a double or a int star, or in your hack this week, pixel or pixel star. Right? Depends on what you're doing. What should it be here? Int. Right? Now that was not the bug because we would have gotten away with that. What we would have gotten away with was the fact that n is an integer. How many bytes does an integer take? 4. How many bytes does an integer take? 4. It would have been the same. Right? But it would have been very bad coding style. Right? So that's not the bug. Next. Oops. Down here. Next. Let's print out what A is. Right? Because if I just allocated a bunch of memory, right? What's in it? Well, it's just a memory address. Okay. How do I get access to that memory address? How do I take a pointer variable and turn it into a regular variable so I can print it out? Print star A. Except that that's just the first element. This is an array of size 4, right? How can I print out the elements of an array of size 4? Print star A and tell it how big it is using an @ sign and then the size afterwards. And it'll print out the entire array. In this case, it's all just initialized to zeros. I haven't filled it in yet on line 45. Okay? So let's go ahead and go next, 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 next. Right? It's going over this loop and assigning random values to each one of those array elements. If I go back and print A at 4, and another trick is you know that 4 is stored in the variable n. You can also use the variable n. Okay, so 3 and 5 were the first two random numbers. Continue. Next, 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 next. All right, we're about to return. Let's print the entire array again to see what we should be getting. 3, 5, 4, and 8. All right. Now, if I hit next, it'll go to the end of the function, return back to the calling function, and it will then print the array. Okay? Next. All right. Segmentation fault. What happened? Let's rerun that. Run. Yes. So what I'll do is I'll go next. Did I set a breakpoint in random array? I think I did. So how do I just jump to that? I can go ahead and go continue. There we go. Oops, no, I did not set a breakpoint. So run. Yes. All right. I want to set a breakpoint. First of all, I don't like this breakpoint anymore. I know that everything is okay up to this point. Let's get rid of that breakpoint. To get rid of a breakpoint, you can go ahead and go clear. Clear line 32. It'll take that breakpoint away. It won't continue the execution of the program, but it will take that breakpoint away. Now what I want to do is I know that everything is okay up to this point, and there's something wrong in that function. Right? So I want to set a breakpoint at that function instead. What was it called? Random array. It doesn't have to be a line number. It can be a function name. Right? And what I can do now is I can run this entire program from the beginning, and it'll jump all the way to the first instance of me calling that function. Okay? Remember that everything's looked good up until line 47, right? So I don't want to have to go next, 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 next a whole bunch of times. So let's set another breakpoint at line 47. And I will jump to that breakpoint by saying continue. Right? Continue all the way down until you get there. Okay, great. Now let's print that array. Now remember that it's a random array, so it's probably going to be a different bunch of values. 3, 7, 4, and 7. Okay? And I'm about to return this. Right, next. Next. Okay, before I print it, let's see if we received that value correctly. Print. And in this context, the array is called ARR, and it should be of size 4. Cannot access that memory. What happened? What happened between returning from the function and this point here? So, first of all, what happened on line 48? I didn't return anything. Again, the wall flag would have found that. Return what? A. Now let's go back to where we returned from this function. Anything wrong between those lines? Does this look correct? Square root of 2. Congratulations, you computed the square root of 2. Did you do anything with the result? No. Generally, if you're calling a function that returns something, what do? You put it into a variable. Did we do that on these two lines? Nope. Congratulations, you created a random array, and then you didn't do anything with it. So let's put that into our variable here. Okay. Save that. Well, it's already saved. Quit this, recompile, and rerun it. In fact, before I fire up GDB here, let's actually run it and see if we get at least output now. I think all of our seg faults will be solved. Okay, great. It looks like it's working. Is that the average of 4, 8, 4, 5? 16, 21. 21 divided by 4 is 5 right? 5.25? Is that right? 6? So, say what? 5.25, right? So did we get the correct answer? Nope. Debug, right? GDB. Okay. Layout, source, set args to 4, and let's go ahead and where did we want to break now? I'm pretty sure that everything is okay up until line 34, so let's break at line 34. Run it, and we're all the way there. Next, print the array, if the array was successfully printed, I assume. And let's go ahead and print what's in it so that we know what we're dealing with. 0, 9, 8, and 3. The average should be 5 exactly, right? Okay. So let's go ahead and see what's happening inside that average function. We're going to step into it. Right, there we go. Now let's go ahead and print out the array that we received to make sure that we received it correctly in this function. Yep, 0, 9, 8, 3. Okay. Now we're going to sum it up. Okay. So let's go ahead and go next, 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 next. I wonder what the sum value is. Print sum. Right. It's 13. Where would we have gotten 13 adding any of those numbers up? I'm not sure. Let's go ahead and go one more iteration here. Okay, now I've got to print the sum again. Now it's 21. Okay. Well, that's because we added the 8. That looks clear, right? But I don't want to have to keep printing this crap out. Right? So what I'm going to do is I'm going to set a watch variable. Watch that sum variable. When it changes, report to me what it changes. The old value and then the new value. So if I go next, next, there we go. The old value was 21 and it became 24 because we added 3. Right? Next, 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 next. All right. So we got out of that function. What are we about to return? Before I return, let's print out the sum. And let's print out n. So 24 divided by 4 is 6. Is that the correct value? Print a at 4 of n. 9 plus, what was it again? 20 divided by 4 is going to be 5. It should be 5, right? But we're getting 24 divided by 4, which is 6. In fact, if I can print out expressions, what happens when I go sum divided by n? It gives me 6. Right? We're about to have a bad value here. Next, print out the average. It's 6. All right, something's wrong here. So I know that something's wrong. Let's go ahead and clear that breakpoint at line 34. Set a breakpoint for average. And let's rerun the entire program from the beginning. We're computing the average of 6, 1, 9, and 6 this time. That's going to be 22. 22 divided... Oh, it's already... Oops. I never set a breakpoint. Break at average. Come on. All right, run. There we go. And refresh so that it redraws it. Okay. Now let's go ahead and print the a at n. All right, 8, 4, 4, 7. We should get, what, 23 divided by 4 is going to be 5.75. All right. So let's set a watch variable on sum. But before we even start here, print sum. We've not even started our loop here yet, and we're already at 4? Where did that come from? Tell me about line 53. It's uninitialized. What was the random value that was assigned to it? The garbage random value that was assigned to it? Turned out it was 4. Right? If we initialize it to 0, we're going to be in a better situation. Right? Quit. Yes. Compile. Run Gdb. Layout source. Set args to be 4. And break at average, because there's still something wrong in that function. Run. All right. So once again, I said I didn't want to go through and, you know, all 4 iterations of this thing. Imagine what it would be like if you actually had to test this with, say, 1 million integers, right? And you had no control over that 1 million, right? You can set a conditional breakpoint. What if I want to just look at that last iteration, right? So let's say break at 54. Did I actually do that? Okay, weird. Break at 54 if I is equal to, what should the last iteration be? So if there are 4 elements, what is the last iteration of I? 0, 1, 2, 3. So break at line 54 if I is equal to, 3. Right? That way I can continue without having to go next, 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 and then overshoot it and have to start over. Right? There we go. Refresh. Oops, it never actually got there. Oh well. What happened? Break at 54 if I is equal to 0. I is equal to 3, right? So run. Next, next, next. I don't know why they can... okay, anyway, next. Let's set a watch variable, watch on sum, and watch I. All right? So as I go through this, you'll see that the old value went from 8 to 16. We have a new array now. A at 4 there. There we go. 8, 8, 7, 1. So 8 plus 8, 16. Now we're on the third iteration here. I goes from 1 to 2. That looks correct. Next, next. 16 to 23 because we just added 7, right? What were the other values? 8, 8, what did I say? 7, 1? Okay, this is why you have another screen over here. Just put it over here, right? You have a whiteboard as well. That you can write something down, right? Next, so it goes from 2 to 3. This should be the last element now. And what was it again? You said 1 for the last one. So it should go from 23 to 24. Great. Next. All right, I goes to 4, which means that we should break out of this for loop. Why? Because we just looked at 4 elements, 0, 1, 2, and 3. Next. Why are we in this loop? Why are we in this loop if I is 4? Does this look like an idiomatic for loop at all? Somewhat. Right? We've been seeing people use commas. Right? We've been seeing people, I think somebody posted a problem that looked like this. All right? I is equal to I. Right? It's always for I equals 0, semicolon. I is less than, oh, okay, too many less than. Right? Less than n. Right? Why? Because it starts at 0. I plus plus. So we were illegally accessing memory. The compiler, the wall flag, would never have picked that up. Right? Valgrind would have. Valgrind would have told you that there was an illegal read of size 4, 1 integer, on line 55. Right? It's not going to cause that much of an issue because, guess what? The sum is still going to be correct. It's just going beyond its array, and we just got lucky that 0 was being stored here. It added 0 to 24, and so it never manifested itself as a seg fault because we got lucky. Right? Next. Next. Now we break out of the loop. So let's make sure that our sum is correct. Print sum, which is 24. Print sum, which is 24. Print n, which is 4. And I'm going to get lucky here because print sum divided by n. It's going to be 6. I wish it hadn't been. I wish it had been 23. Tell me what's wrong with that line. It's going to end up being right, but for the wrong reasons. It's because 6 goes into 24 exactly. Right. What's wrong? Truncation. Double. Right. So even if you don't apparently see it right away, at least you can narrow it down to one line of code and then sit there and stare at that line of code. Right, and ask yourself, have I ever seen any of these problems before? Integer truncation, off by 1 errors, right? Roll through all the list of things and pitfalls that we've been talking about for the whole semester and think, do any of them apply here? Do any of them apply? I think that was it. GCC. And then we can run a.out with 4. 5.5, that looks right to me. 22 divided by 4, yep. Run it again. 2.5, that looks good too. Right. Run it again, run it again, run it again, run it again, how many times you want. Test it for 10,000 integers. If this is correct, what do you think would be our expectation? By the way, the way that it generates these things is it's random numbers between 0 and 9. So if you generated a massive amount of numbers between 0 and 9, what would the expected average be about? Oops. Don't want to do that. 4.46, 4.48. It seems like it's hovering around 4.5. Why? 0 through 9, what's the average of 0 through 9? 4.5. Right? So there's another way that you can test it and give it the, the old sniff test, right? Yeah, it looks fine. Are you going to debug 10,000 things, though? Nope. So let's fire up GDB one last time and show you what something that I talked about recently. But we did it on a small scale here. Layout source, set args to 10,000 integers. Right. Now let's go ahead and set a breakpoint at average. Right. Oop, break at average. Right. Sorry. And then run. Right. All right. Refresh because it printed refresh because it printed all that stuff. Now that loop right there on 54 is about to go for 10,000 iterations. Do you want to sit there and go next 10,000 times? No. Let's find out what happens in the middle of it. Break at line 55 if I is equal to 5,000. Right. Continue. Process, and then it stops when it hits 5,000. Print I. Right. So you can jump ahead. Okay. Clear 55. All right. We've deleted that breakpoint. Let's find out what happens at 9,000. Break at 5,000. Break at 55 if I is equal to, well, the last iteration, 9,999. Let's go one more. Right. We'll fast forward almost all the way to the end. Continue. There we go. Print I. It stopped at 9998. Now I can go line by line to see just what happens at the end of the loop. Right? Very, very powerful tool here. Right? Okay. But it's probably okay. Right? All right. Questions on this so far? Then, my suggestion would be to find a GDB cheat sheet, or you can use. I use a GDB cheat sheet. I just found one, and put it up on my desk. But if you want to use my GDB cheat sheet, here you go. Here's everything we just covered. Right? You can set command line arguments using set args and then 5, 10, 20, whatever. You can view your code using layout source. You can sometimes this display screws up, so you just go refresh. Right? You can set a break. I think I jinxed it this morning. And this morning's class, I've noted that ever since I moved over to code spaces, I've never had to do that. And then right in the middle, like right after I said that, it started screwing up, and it continued to screw up today. So I don't know why, right? But I jinxed it. You can set a breakpoint, break line 12, or break at a function. Or if you've got multiple files, you can say break in file.c at line 26. Okay. Okay. You can remove a breakpoint using clear. All right, clear that breakpoint at line 12, clear the breakpoint at main, etc. You can print variables or expressions. Right? You can print variable name or n times x. Anything that you can write in C, you can write and evaluate in GDB. Right? You can print an entire array of values as long as you know its size. Array at 8, for example. You can use pointer arithmetic to jump to the middle of an array and print out only certain values. You can also print out individual values, right? I didn't show that, but you can do that. Or individual values using, say, print a sub 3. Right? Anything that you would do in C, you can access in GDB. You can quit, which is the most important thing, right? You can pause the running of an infinite loop or very long running program using Control-C. If you were at the regular command line, Control-C would kill the entire program at dead. But if you're simulating it in GDB, it doesn't kill GDB, it pauses the program. So if you're stuck in a loop, right? Which loop am I stuck in here? Poor man's debugging would have print forever, right? But this one, with GDB, you can go ahead and go Control-C and it'll stop wherever it is in that loop. and then you can next to see why you're in an infinite loop. You can watch for variables, and it will tell you when they change and what they were and what they are now. You can continue to the next breakpoint using continue. You can go to the next line, or N for short. And you can step into a function using step. I think you can use S for short, but all of these common commands can be shortened to one single letter. But next is the only one I do it with. Right? You can set conditional breakpoints. Break at line 10 if x is equal to 21. You can combine any logical statements that you want. If x is equal to 21, or y is greater than 0, and z is equal to null. Any expression that you can write in C, you can write as a conditional breakpoint as well. All right? Okay. Any questions on GDB? Otherwise, what was the comment? I'm so tired of this programming. It's so long road. English, I think it's just spam. English and French channel for languages learning. Okay. I'm sure. I'm sure that that's just spam, because I'm tired of whatever this is. Come to my channel for learning French, right? All right. Any questions? All right then. Remember, we've got your midterm on Wednesday, so prepare yourself for that. Best by getting Hack 7 done. Just a second.